All right, so now at long last, we're ready to start the new material, which is chapter one, of course. And the focus of this chapter is on something called limits. And we're going to use limits to derive a lot of important results in Calc 1 and in Calc 2. And it's an important topic in its own right. So we're going to start with section one. This is, if you look at the slides in Brightspace, you'll see that they're broken up into sections. So chapter one is broken up into four sections: 1.1, 1.2, 1.3, and 1.4. They're all done that way. So here in section 1.1, we'll be just basically briefly introducing some of the topics that we'll be covering in the course. And then in part two, 1.2, I should say, we'll be actually calculating limits, or at least introducing them. Okay, so they're going to start now in the very beginning of this chapter. They're showing us some of the things that you have to look forward to in this chapter. Like they're first introducing the whole idea of calculus. It has a very interesting history. It was mainly developed by two rival mathematicians. One was Sir Isaac Newton, who you've heard of before from your physics classes, and the other was Gottfried Leibniz in Germany. And they both invented calculus independently of each other, more or less at the same time. But Newton, in particular, was very secretive about his research, and so he didn't publish his results for quite a long time until after he'd finished it. So the thinking now apparently is that Newton may have gotten there first, but just barely, and neither one of them knew about the other until they started publishing their work. So some of the notation that we see in calculus is coming from Newton, and some of it is coming from Leibniz. Those are the two main developers of the field of calculus. Now they're going to show you some things that you could solve for with calculus. What they want you to see here is they just want you to get the idea that there's different ways of approaching these different problems and that it's probably going to be easier to use calculus than other techniques. I think this is the purpose of these drawings. Um, and so we'll run across these different applications as we go along. We can save that for later. So we'll start with this notion of the tangent line. Now, of course, we're going to see tangents all the time in calculus. All right. It's an important idea. And if you remember from your travels, a tangent line is a line that touches a curve at exactly one point. Okay. So the word tangent here in this context means that the line that we're looking at, or the curve, touches at exactly one point. And often the slope of that tangent line is what we're interested in. Okay. That will prove to be hugely important as you see. Now, sometimes though, we have a line that cuts through a curve at two different points. Let's say we have something like this, and this is now known as a secant line. Okay, so the word secant means that it cuts through twice. The tangent means it touches it precisely at one point. Okay, so we're going to end up needing both of these throughout calculus. No matter how far you go in calculus, you'll be using these on a pretty regular basis to derive results. And here, for example, yeah, they're just reminding you what I just said. That blue line there is a secant line, and if we what's interesting here is that what we'll see is that if we get 2 points that are progressively closer to each other, eventually the secant line will converge to a tangent line. Okay, so in other words, like here, if you notice, these points are pretty far apart. But if I had 2 points that were very close to each other, let's say I'm looking at these 2 points, and they're getting pretty close to each other. And so you can see that they're getting awfully close to the tangent line, which is, let's say, right here. And so that will prove to be important as we shrink up the distance between the 2 points. The slope of the secant line will eventually be the same as that tangent line. That's kind of a hint as to what's coming up. Um, so here, they're trying to show us the slope of the secant line rather. And in terms of this graph, what would that be? So of course, the slope of this secant line will be, so delta y is the difference, the vertical difference between the two y coordinates. Delta x, by the way, is just meant to represent the difference between x1 and x2. Okay, so then we have f of c plus delta x, and then from that we subtract, actually, I started to draw the wrong thing here. We subtract f of c. By the way, they're using the notation m with a little sec here to remind you this is the slope of the secant line. And then the difference between the x's is just delta x, which is c plus delta x minus c, but that reduces to delta x. Okay, so as like I said, as the distance between the x's gets smaller, in other words, as delta x gets smaller, which we'll write like this little arrow means approaches or converges to. The slope of the secant will eventually match the slope of the tangent line, okay, to that curve. Okay, area problem. Now, and by the way, we can't say any more about this until we get to that part of the course. So just, I know it seems like I left you hanging there, but this is one of the techniques that we'll need to derive some very important results. Okay. And then we have this area question. Suppose we have a curve, could be anything, looks like a cubic function. And what if I need to know for some reason the area under the curve between these two endpoints? Now, it's not going to be easy because, of course, you can see while the two sides are straight lines, so is the bottom, but the top is not. It's a curve. So what do we do? Well, that's going to be an important question. And so what you can think of this as, imagine drawing these rectangles underneath that curve and using their area as an approximation to the actual area under the curve. And you can see what they're getting at here is that the number of rectangles as it grows, the area of the rectangles will get closer and closer to the area of under the curve because like here there's these enormous gaps. Well, everywhere you see this sort of peachy color, that means that we're missing something. And in fact, up here, if you look carefully, you'll see that here the rectangles are actually a little too tall. So here you can see that it looks like the actual area and the area of the rectangles is even closer. And if we keep increasing the number of rectangles, eventually the two will match each other. We'll have the exact area that we need. Um, so here, yeah, see what they're, but they do want to make one important point here, though. There's two different ways of putting those rectangles under a curve. Okay, we just have to be aware that there are two different ways of doing this. And what are those ways? Actually, let me try this. I can just about fit them in there. Yeah, I was hoping to get them to be identical to each other. So, in other words, when you form these rectangles, there's a left endpoint and there's a right endpoint. So, if the left endpoint touches the curve, this is what we have. See now, well, with some of these, it's hard to tell what I'm doing. But you can see that these are too low for the most part. Whereas if I do the opposite, what if I let the right endpoint touch? Then at least in this case, the rectangles appear to be a little too tall for the most part. And certainly in this case. So in other words, in the left-hand side, the left endpoints touch the curve. And then we describe the rectangle from there. And then over here, it's the right endpoints that touch the curve. Now, as it turns out, if we keep increasing the number of rectangles, the area of the rectangles on the left and the right will actually match each other, and they will in turn match the actual area under that curve. So, what it basically means is it doesn't matter which approach we use. If we have enough rectangles, we'll have the correct area. Okay. So again, we'll be getting back to this very soon. Okay. So you can see now here, ooh, they did a nice job here. You can really see the difference between the two. The actual curve is on the left. That sort of peachy color is what we're looking for. On the left, now they're calling these inscribed rectangles. The ones on the right are circumscribed. And so you can see the ones on the left are a little too short. The ones on the right are a little too tall because of the way they're defined. But if we keep increasing the number of rectangles, these two will exactly match each other, and they'll both match the correct area under that curve. Okay, so you're probably wondering, why are we doing this? Well, you'll see. You'll see soon enough. Don't worry. All right. So now that was 1-1. We're ready to start looking at limits. Okay, this is 1.2. Oh, sorry, wrong one. We need 1.2. There we go. Now, limits are an interesting idea, a very important concept in calculus. And so here they started us with a very tricky case. I'm not sure if that was such a great idea, but here's what they want us to start with. Um, we've got this function, and you can see there's going to be an asymptote in there because we cannot allow the denominator to be zero, which means one is not part of the domain of this function. So it says here, use standard curve sketching techniques. Why don't we go visit our friend Symbol Lab and see what this is all about? X cubed minus 1 over x minus 1. Now, the whole purpose of this discussion is this. You see, there's this little hole here. Um, because we know that if x equals 1, the function, there would be division by 0, so we can't allow that. All the other points are intact, okay? So I'm going to copy this with this thing snagged that I have. Actually, I think with a Mac, you don't really even need the snag, but all right, let's see how it goes. All right, so first, actually, let me make a note here. We are now starting our discussion of limits. All right, so we'll start whoops, with this function. And you can see, I think they chose this point because you can see the point that's missing is 1 comma 3. Okay, um, now, what do they want us to notice here? If I want to determine the value of that point, um, as I get closer and closer to 1, so imagine yourself substituting values of x into this function. We start with the values that are less than 1, like -2, -1, 0, etc. As we get very close to 1, but we don't quite reach 1, I think there's a chart here to illustrate what that is. Yeah, here it is. In other words, if you notice, they're having you fill in a bunch of values for, giving you a bunch of x's. They want to know the corresponding function values. Oh, sorry, I was looking at the wrong one. It's this one. Um, so here's 1. So as we start substituting values of x that are slightly less than 1 into the function, if you look at these numbers in the bottom, you'll notice, in fact, let me copy this real fast. So in other words, this little arrow is meant to indicate that as I start substituting values of x that are less than 1, the values of y are not only increasing, but if you notice, they keep getting closer and closer and closer to 3. Okay. They've got a question mark there for a reason. If I go from the other direction with the larger values from this side, um, larger values of x, you notice that these numbers are getting closer and closer to 3. So in other words, starting with large values of x and reducing them awfully, awfully close to 1 on this side, this number is really close to 3. Coming from this side, as the x's get larger, but never quite reach 1, the function gets really close to 3. So what we say here then is that while we can't actually directly substitute 1 into this function, we say that the limit of this function as x approaches 1 is 3. Okay. Now, again, you can't, it's kind of like imagine there's a big hole there. It's like a big pothole in the road. You can step as close as you want to the edge, but if you step in there, you'll just fall down. Um, so we can get really close to it, but we can't actually reach x equals 1 and x equals 3, but we're getting closer and closer and closer. So that is known as the limit. As x approaches 1, it is equal to 3. And we write it in a very interesting way. So that means that's a shorthand way of saying that as x approaches 1, the limit of this function is 3. And we can also calculate this individually from the two different directions. Over here, we call this the limit. As x approaches 1 from the left, all right, that little minus doesn't mean -1. It means we're approaching from the left. And then for this one, we say that the limit as x approaches 1 from the right is 3 as well. So in other words, we have a limit, which, and we also have a limit from the left and from the right. Now, in general, what's going to be true is that the limit coming from the left and the right have to equal each other for the limit to exist. Okay. If they're approaching two different numbers, then we do not have a limit at all. And that can happen. You can get these weird cases where, let's say, you have something like this, where there's a discontinuity here. And let's say that when x equals 1, for the first, this lower piece of the function, y equals 2, and over here it's 3. And so what this is telling us is that the limit, as x approaches 1 from the left, is 2, but from the right, it's 3. Oh my God. And that means that the limit does not exist. Okay. They have to be equal to each other. The function is discontinuous. Okay. But anyway, let's see where they're taking us with this example. So this is just the general expression for the limit of some given function as x approaches c is equal to L. So I think you'll see it makes sense. It's consistent with what we were just doing, but we're just using variables instead of constants. Now here's another one. They want us to go in and fill in a bunch of x's. I don't think there's any need to do that right here. What I would like to do though is show you the graph though, and we can see visually where it's heading. Um, let's go back to Symbol Lab. Yeah, I don't think we need to waste our time doing all these calculations. Um, that's kind of pushing it. Whoops, that's not what I wanted. There it is. All right, here we go. So we have um, the ratio. Oh, yeah, no, we're just going to draw the graph. We have the ratio of x squared minus 3x plus 2. Whoops. all divided by x minus 2. So yeah, this is what they're getting at. You see right here, this is the point 1 comma 2. Okay, which means that the limit as we approach from the left and the right is equal to 2 because they're both equal to each other. Okay, in other words, you can see they're both heading to the same point. There's no discontinuities except for that gap. In other words, the curve itself doesn't break apart. So if you did fill in all these numbers, you would see that they're getting progressively closer um, to 1. Actually, it's 1. Y equals 1. The limit is 1. If you plug these in, these numbers coming from either side are getting progressively closer to 1. Okay. All right. Now, sometimes, now here's an example that I was just referring to. If you look at this graph, you can see um, here the limit doesn't exist because it is different coming from the left and the right. So this is one of those bizarre step functions. Here, coming from the left, you can see we're getting awfully close. As x, by the way, this is as x goes to 0. So as x gets closer to 0 from the left, um, we're getting awfully close to y equals -1. But coming from the right-hand side, it's either we're getting close to y equals +1. So we would say that the limit as x approaches 0 from the left is -1. As it approaches 0 from the right is +1. And since the two do not match, we say that the limit does not exist. Now, if something like this shows up in WebAssign, they often will ask you to abbreviate something like that. They'll tell you to write the letters D and E or something like that. So keep an eye on that. They have their own ways they want you to enter your information. Okay. Now, this is a very, very formal definition of what the limit means. I'm going to run through it with you real fast. I don't know if they're going to actually ask you to do any problems based on this. It's very intense, to say the least. But we're going to run through it once just so you get what this is all about. Okay. In other words, this is with all general terms. There's no constants listed in this particular discussion. So if it seems very complex and overwhelming, that's because it is. But you should have seen this at least once when you're working with limits. Even if you never need to think about this again, you don't want, you always want to understand the basic foundations of where a concept comes from. Um, so anyway, here's the graph we're going to be working with. By the way, this is the Greek letter epsilon. And this is actually the lowercase delta. You've seen the triangle being referred to as delta. The difference between the two is that the triangle is the uppercase version, and this one is lowercase. Okay, So what in the world is going on here? Well, here's our x. And see, now you can see there, just like what we were seeing before, there is a point here, C comma L. And the limit of this, so in other words, the limit of this function as x approaches C is L. Just keep that in mind, whatever those numbers are. But what does that mean? So you have to think of epsilon and delta as extremely small numbers. And so what they want you to do is this. The formal definition is this. Being this, what I'm about to write is equivalent to saying y f of x, I should call it f of x to be consistent. F of x is in the interval, as you can see over here on the graph, from L minus epsilon up to L plus epsilon. So this is just the more formal way of writing that. Okay, mathematicians love their formal notations. And then this statement means that x is in the interval uh-huh. Okay. Well, already it seems very bizarre and abstract. So what we can do here is use some numbers. I think the only way this is going to work is if we use numbers. So let's try y equals 2x minus 5. Or uh, let's call it f of x again. Now imagine that we're interested in knowing the limit as x approaches 3. In this case, when x is 3, y is 1. And what they would like us to see, to prove that this is actually the limit, it goes like this. By the way, before we go any further, let me just remind you, let me grab this graph one more time so we can see it as we're going along. So for every possible value of epsilon, we can find a delta, positive delta, such that So assuming that X is somewhere in that range, then that guarantees that, and that statement, of course, means that f of X is in the interval um, L minus epsilon up to L plus epsilon. So, and again, you're saying, what is going on here? I think once you see the numbers, that'll probably make a big difference. So let's pick the numbers. Uh, how about, so in other words, we're going to choose this interval between 0.99 and 1.01, which means L is 1 and epsilon is 0.01. And then down here, the corresponding x's can be derived in the following way. Now, we can figure out just by setting the function equal to 0.99 and 1.01 that these x's are in fact 2.995 and 3.005. Okay, so in other words, if you, let's say you plug into your calculator um, f of 3.005, just as an example. Oh, I'm sorry, what did I do? No, it's not 005, it's 3. Well, what do you know? It's 1.01. So that becomes, you remember from this graph up here, that's C is the 3. And the gap here, C minus delta, being 2.995, implies that delta must be 0.005. And the same thing is true up here. This is supposed to be C plus delta. And that would be 3 point. And it is. Okay. So assuming that C is in fact, I mean, X is in that interval, this is the bottom line right now. If C is in the interval, or I'm sorry, X is in the interval, then f of x is in the interval 0.99, 1.01. And so the logic here is that if I keep shrinking up the interval for x, I'll also keep shrinking up the interval for f of x. And so that's kind of where this is going. As I keep letting these numbers, the deltas and the epsilons get smaller and smaller, x is getting close to the 3, and f of x is getting close to the 1. Okay. And that's what it means to be a limit. Now, if you didn't find that terribly enlightening, just be aware that this is, the formal definition of limits. I don't know if you're going to have to use this in any of the mind WebAssign problems. I don't think so. But again, like I said, it's good to understand what this concept really is all about. It just means that as we get closer to x, as x gets closer to 3, f of x is getting closer to 1. That's really the bottom line. Okay. So it's a very, very convoluted approach to demonstrating that x gets close to 3, f of x gets close to 1. So yeah. Okay, so that was our theoretical discussion for the day. Now we get to do actual rules. We're going to define several rules for calculating limits, and I think you'll find that to be actually quite straightforward. It's not a very complicated thing to do for the most part. Some of the messier functions, of course, will be difficult, but most algebraic functions it'll be very simple to calculate their limits. For example, all right, let's skip over the rest of this. Yeah, this is that's all we need for that. Okay. So now we're ready for section 1.3, where we get to actually do this. Um, so properties of limits. Sometimes, in many cases, you can find a limit with direct substitution. Okay. Unless there's something very strange about the function, often that's all you have to do. Okay. So just as a quick example, one way of potentially at least doing this is now, of course, as you could probably guess, if this approach leads to, let's say, division by 0 or something like that, then of course we have to try something different. But in many cases, that's all we have to do. And this is the formal way of writing that. Okay. But let's do an example. Oh, look at those. Um, I tell you, I'd rather do some actual numbers. Let's try this. So in this case, it's direct substitution. That's all you need to do. Wow, that was easy. And if you were to draw a picture of this, you would see that that's what's happening. It's just the limit is just, it's 8 because when x equals 2, y equals 8. It's as simple as that. Doesn't matter if you're coming from the left or from the right, you'll always get the same answer. Okay. Now for these are very simple cases. The limit of a constant is equal to a constant. Here, the limit as x approaches -4. We just plug in -4 for x. And then here, as we take the limit of x squared as x approaches 2, again, you just substitute 2 for x, and you'll end up with 2 squared, which is, of course, 4. Okay, so these are very simple cases. Now, there are algebraic properties that we need to know, but they all are completely consistent with what you know about the real numbers. There might be one or two that may not be super obvious, like this first one. Um, Actually, I'll tell you, let me copy the entire list into here. Oh, by the way, if you notice, they're assuming at the top the limit of f of x is L and the limit of g of x is k. So I guess they'll stick with just letters for now. So if the limit as x goes to c of f of x is L, and for g of x, okay, so we're assuming that the limit is, in both cases, we're approaching c of f of x is L, g of x is k, then the limit of, they're going to call it b is some constant. You basically factor out the b, that's all. Okay, so remember the b is a constant. For addition and subtraction, it's exactly what you'd expect. In fact, I'm going to consolidate these into a single statement, which means if I'm adding, then I get L plus K. If I'm subtracting, I get L minus K. Multiplication, same thing. I mean, it's just exactly what you're thinking. Wow, that was easy. And then the division, of course, assuming that K is not 0. All right, well, that's easy. So let's see what kind of examples. Here we go. So let's try one of these. Finally, we get some actual numbers. I like numbers better. Okay, so I broke it up into two pieces. Now I'm factoring out the constant. In the first case, I'm just doing a direct substitution. In the second case, the limit of a constant is a constant. Okay, and that's it. That's all there is to it. Wow. It's almost shocking how simple it is. All right, well, it won't stay simple forever, but it's good to know that these basic ones are very straightforward. Okay, what else do they have for us? Oh, they want you to see the graph, and you can see it's just that point 219. Okay. Yeah, well, this is pretty much exactly what we just saw. Um, oh, okay, let's try this one. So again, this you're just using direct substitution. There's no risk of ending up with division by zero. So we can just go right ahead and plug everything in. Wow, that's all there is to it. Yeah. And that's it. And then, they're going to show us the curve, and that means we're looking at the point 1 comma 2. Square roots, nothing changes. For example, the limit, again, it's just that simple. Oh, now these are composite functions. We went over this the other day. If, okay. So what they're saying is that the limit of g of x, this is going to be a little bit messier, as you can imagine. That means that the limit of the composite function is going to be f of the limit f of L. Okay, so that'll make a lot more sense when we see an example. Here we have the cube root. By the way, sometimes this isn't even really necessary. Like here, you could see direct substitution would take care of this one, but they want to illustrate this principle. Cube root of 2x squared minus 10. So if you can think of g of x would be what's under this cube root sign. F of x would be the cube root of x. So the limit of this expression, uh, so L is the limit of just the 2x squared minus 10, which is 18 minus 10, which is 8. Therefore, oh, sorry, that doesn't go down there. It goes over here. Now, according to the result we had up here, it's f of L. So since L is 8 and f of x is radical, the limit is the cube root of 8, which is 2. But it just seems it's very kind of convoluted. All you had to do in the first place. Oh, they probably chose it like this on purpose to make sure you could see that there's two different ways of getting to the same answer. If you just plugged in the 3 in the first place, you would have gotten the right answer. Okay. So, trig functions. But you know what? Again, if you notice in every single one of these cases, you're literally just replacing the x with a c. So they're not complicated at all. That's a relief. Let's see, what do we have? Oh, okay. So what they're doing is they're obviously complicating them a little bit. So the limit as x goes to infinity of tangent x. Now, I am going to have to go get my calculator. I happen to have a wonderful TI-84 right here, which will make all this so much easier. I don't have these all memorized. There's certain ones you'll see over and over again, but then, why not just at least double check with this thing? So I'm just going to confirm the tangent of 0 is 0. Yes. And by the way, if you're using this calculator, make sure that when you're using trig functions, that you're in the right mode. There's a radian mode and there's a degree mode. And if you go to the mode button, which is in the extreme upper left-hand corner here, and it's backwards, but you can see it right there. Um, in backwards mode, it's E-bomb or something like that. Click it on, and you'll see there's a huge selection of modes. The fourth from the top is the one where you choose between radian and degrees. So you go down with your arrow key, go to the one you want, hit enter, and you're all set. Otherwise, you'll get the wrong answer and you won't know why. Now, this next one, oh my God, we're back to radians. X cosine X. So I'm going to make a little switch here on my calculator. Okay. Now, the first one is just pi. The second one is cosine pi, which is -1. Well, that was easy. Well, not really, but and then the limit of sine squared x as x goes to 0, that is. If you want, you could write it like this. And the sine of x, a zero rather, is zero. Well, that makes things easier. All right, great. Okay, so where are we? So, strategy for finding limits. Now, here they're going to give us some more complicated cases. So, since it looks like our time is up, I think we'll stop right here. And next time we meet, we'll look at some cases for finding more complicated limits. So, hopefully, this wasn't too overwhelming for the first new session. The rest of it was review. Remember, this is the first time we've seen anything completely new. But don't worry, once you get practiced with it and get used to it, it'll be very straightforward. Limits are not that complicated. Once we get some more practice, you'll see it's very straightforward. Okay, so anyway, we'll stop here and I'll see you next time.